Experimental data on the Fick diffusivity of binary mixtures that experience phase transition show that the Fick diffusivity values reduce to zero as the concentrations approach saturation. As an example, let's look at glycine water, diffusivity of glycine water shown by the green squares here, or diffusivity of urea water shown by the red circles. We note that the experimental data on the Fick diffusivity reduced to zero as conditions approach phase saturation. We examine the consequences of such behavior of the Fick diffusivity and use the Maxwell-Stefan theory for molecular diffusion to quantify the concentration dependence of the Fick diffusivity. We also demonstrate the phenomenon of spinodal decomposition that occurs within the spinodal envelope. For background theory, I refer you to my publication in Chemical Engineering Science 2019. Watch also other videos, diffusion and liquid mixtures, uphill diffusion, what drives diffusion on my YouTube channel. Let's begin by analyzing diffusion in binary mixtures of components 1 and 2. Let U1 and U2 represent the velocities of motion of components 1 and 2 in a laboratory fixed reference frame. U is the molar average mixture velocity. Since the chemical potential gradients are constrained by the Gibbs-Duhem relationships, only one of the chemical potential gradients is independent. The mole fractions sum to unity, and therefore there is only one independent measure of composition. In the Maxwell-Stefan formulation, the force acting per mole of species 1 is balanced by friction species 1 experiences in undergoing relative motion with respect to species 2. The frictional term must be proportional to the composition, and we take that proportionality to be represented by the mole fraction of component 2. The physical significance of the Maxwell-Stefan diffusivity, where we use the symbol D with a line through it, is that it represents an inverse drag coefficient. The force acting per mole of species 1 is a negative of the gradient of the chemical potential with the units newtons per mole. The Maxwell-Stefan equation can be reformulated in terms of the diffusion flux, which is defined as the flux with respect to the molar average reference velocity Vm is the molar volume of the mixture. Rather than use the chemical potential gradient as a driving force, it is convenient to define a thermodynamic correction factor given by this expression, which quantifies departure from ideality. Indeed, if the activity coefficient is unity, gamma is equal to unity. And the Maxwell-Stefan equations can be recast into the form flux of component 1 is proportional to the mole fraction gradient of component 1, and the constant of proportionality is the Maxwell-Stefan diffusivity times gamma. Therefore, in comparison with the Fick's law, we note that the Fick diffusivity equals the Maxwell-Stefan diffusivity times a correction factor that quantifies departures from thermodynamic idealities. Let us examine diffusion in the binary mixture of methanol and normal hexane at a temperature of 313 Kelvin. The Fick diffusivity is plotted here as a function of mole fraction of methanol. We note that the Fick diffusivity decreases by about an order of magnitude as composition of 0.5 is approached from either end. By dividing the Fick diffusivity by the thermodynamic correction factor gamma, we obtain the Maxwell-Stefan diffusivity, and that Maxwell-Stefan diffusivity is practically independent of composition. This is the persuasive advantage of using the Maxwell-Stefan formulation, because it shows a more predictable composition dependence than does the Fick diffusivity. Now let's try and understand this reduction in the Fick diffusivity value as shown by the experimental data. The mixture of methanol and hexane undergoes phase splitting at temperatures below about 308 Kelvin. The green line represents the binodal curve, which is defined by the minimum in the Gibbs free energy, say at 290. These are the 2 points here where the partial derivative of G with respect to the composition x1 is 0. Those are the points. So plotting the minima in the Gibbs free energy versus composition curves, we can construct the binodal curve. The red line represents a spinodal curve. These are points at which the thermodynamic correction factor is 0. This is the same as stating that the second derivative of G with respect to the mole fraction is 0. So those are the points representing the spinodal curve. Within the region, the mixture will undergo phase splitting. Say if we take a composition here of 0.5, subject to a small perturbation, the mixture will yield a hexane-rich phase and a methanol-rich phase. The area between the spinodal curve and the binodal curve is a metastable region. A different way of expressing the phase splitting phenomena is to say that the Fick diffusivity is negative in this region. Now, the sharp decrease in the Fick diffusivity is due to the fact that at this temperature 313, we are very close to the two-phase region. Now, the phase splitting in liquid mixtures occurs too quickly or too fast in order for us to follow the diffusion trajectories. Diffusion in metallic systems occurs slow enough for us to monitor the composition trajectories that are followed during phase splitting. In order to demonstrate that, let us consider the binary mixture of iron and chromium using the thermodynamic data on the free energies, binding sets, and entropy of iron chromium mixtures. We can construct the phase diagram shown here. For all temperatures below 1100 Kelvin, the system splits into two phases. The green line shows the binodal curve, and the red line shows the spinodal curve. Along the spinodal curve, the thermodynamic correction factor is 0. And for the region indicated in gray, the thermodynamic correction factor is negative. It also suggests that the Fick diffusivity is negative in this region. That would lead to uphill diffusion. In this graph, the activity of each of the components, iron and chromium, are plotted against the atom fraction of iron. It's interesting to note that for iron, the activity gradient of iron is opposite in sign to the atom fraction gradient of iron. The same is true for chromium. The activity gradient of chromium is opposite in sign to the atom fraction gradient of chromium. Let us take a composition of 0.5 in this region and subject it to a small perturbation. Following up from the previous slide, let us take a system consisting of iron chromium at a composition of 0.5 in the unstable region. I draw only the chromium atoms here. Initially, the compositions are uniform in two regions, say within the unstable region. We subject the system to a small perturbation which leads to a higher amount of chromium in the left compartment than in the right compartment. Since the Fick diffusivity is negative in this region, this leads to a situation where the diffusion will be up the atom fraction gradient of chromium, and this would lead to an exacerbation of the segregation phenomena with more chromium atoms migrating from the right compartment to the left compartment. So this is a self-accelerating process where uphill diffusion will increase the segregation of chromium in the left compartment and lead to a excess in the atom fraction of iron in the right compartment. It is useful at this stage to follow a simulation of this phenomena where we see that the segregation producing islands of chromium form within a matrix of iron that is indicated in red.